Hello, everybody. It's really good to be with you. Now, I don't have any references to movies, but I do have references to computer games. Right. So the title of my talk is Wireless Systems, Self-Driving Vehicles, and Digital Twins. So I'll attempt to straddle all those areas, and I'll try to pick up some areas of overlap. I've just looked again at my slides. I don't mention AI anywhere in the slides, but there will be undertone of AI across the board. Okay, so I will start with the concept of digital twins. Digital twins is one of the hottest topics that is currently around. I'll try to make a case why this is becoming even more important as we go along for wireless systems or connected automated mobility and many other disciplines. Here I've picked up a definition by IBM. I'm not going to read it. I just want to point a few keywords in there that I think very succinctly describe what's the key idea here. It's not just a mirror of a real system. It's essentially an object, a living object that lives together with the real object, evolves together, and acquires the features of the real object. So here's very brief history of the digital twins. All I want to say is, I guess that's not going to be too surprising to you, is digital twins do not represent a revolution. It's more of an evolution. And it all started in sort of 1960s, whenever compute resource was available, or compute resource was available to do some fairly decent computations. Over the years, it progressed slowly. I pick up here a few milestones on the way. It's interesting to note that the term itself, digital twin, appeared in the published form in early 2010s, but it traces back to 2004. Apparently, was used in the presentation. And off we go to the current day. Well, the Gartner lists digital twins for the last 3 years as a top 10 technology trend. So you can be sure we are hitting the hype, top of the hype curve. But what I want to say is there's a good reason for that, and hopefully I'll show you something slightly different. Before that, just quick slide to show where these ideas have percolated. There's a number of engineering sort of verticals, sectors, that you will not be surprised that you will find the digital twins there. But you can also find it in a medical domain. You may have heard there's a big European project called the Human Brain Project. But there's also many other smaller, less known projects that attempt to build digital twins of various organs, for example, heart. Well, but what I really want to argue here is slightly a different approach to digital twin and why they may be useful in our research and development of wireless systems. Right. So the reason is that we have currently a bit of a problem with machine learning, with AI. AI, machine learning, is making, it's been mentioned in the previous talks, and there's a good reason for that. But the current crop of techniques really is at least those success stories are supervised learning techniques where it's still great and we can use them. But the trouble is that with most of the real world data, the data is not suitable to be used with supervised learning techniques. The world is full of messy data, unorganized, uncurated, and unlabeled. And many companies go to great pains to label the data. To quote one example, Tesla, when developing their own autopilot, the team of labelers is about 10 times as big as the team of machine learners. So it's a huge problem. So real world is messy. Now we could try to do the old way, crack the fundamental physics, develop solutions, find E equals to mc squared for your problem. But again, the trouble is the world is too complicated to do that analytically. What's left? Well, develop better machine learning strategies, better AI, and indeed the community is pushing exactly in this direction, and there is no effort spared in order to develop new techniques, new self-supervised learning techniques, unsupervised. But in essence, this is still in its infancy. I should signpost there are some success stories. So, for example, in NLP, natural language processing, GPT-3, you may have seen in public domain. It's great, and that's an example of a success of self-supervised learning. But what I want to argue here is that digital twins can actually step in and provide this kind of bridging technology. So while we're still waiting for this amazing self-supervised learning, unsupervised learning, which who knows how long it will take, we can use digital twins in the meantime. And here's one example of why that strategy works. And in fact, there will be some other niche applications where it will always work. So here we have AlphaGo example. So here's my computer game example. And in my mind, this is an example of digital twin. Again, I'm sure most of you would have seen press reports about 3-4 years ago. AlphaGo beat Lee Sedol, the champion of game of Go, the ancient Chinese game. I'm going to talk about here a newer generation of that version. So specifically AlphaGo Zero. So AlphaGo Zero is the later version, and the difference is that whereas AlphaGo, the version of Lee Sedol, was trained on many, in fact, thousands of games of Go that were fed. So essentially, loads of data from human-played games were fed into the algorithm to pre-train it. AlphaGo Zero did not use that. AlphaGo Zero starts from scratch and achieves amazing levels of performance. It did not make much news. I think it's simply because, it's very hard to show it. There are no humans left to be beaten. AlphaGo Zero could only beat AlphaGo. But here, the main kind of message take home I wanna say here is this is an example of turning computations into data. We don't have good labeled data, but we can use computations to make up for it. Labeled data is expensive. Computations, on the other hand, are becoming cheaper and cheaper. I've got here on the right-hand side is a bit of a schematic of this algorithm. I put it there because I could not resist. It's a marvel of an algorithm, but obviously we don't have the time to go into details. I just want to say that AlphaGo Zero is a beauty that links together deep neural networks and kind of more traditional search-based techniques. Kind of multicolored tree search on the top and a neural nets at the bottom, and it's absolutely amazing stuff. Another example I'd like to put here is self-driving vehicles and how digital twins are used in connected and automated mobility. So I'm sure you've seen in the news Waymo is out there testing their vehicles. What is reported less often is the fact that Waymo is actually doing much more tests in software, in essence, in a digital twin. And in fact, Waymo recently admitted that during COVID lockdown, they did 20 million miles a day, which is about equivalent to 100 years in the real world testing. So overall, so far, Waymo has done 20 million miles on the roads and 15 billion miles in digital twin. And the reason why you want to be doing a lot of that stuff in software is because, in fact, it's very difficult to learn from the data acquired from real life, especially in kind of a safety-critical application like automated vehicles. Most of the miles you clock on the real world are actually boring miles. Nothing ever happens. If nothing ever happens, you don't learn anything. You do not adjust the driving policy because there's no point. What's interesting is all the edge cases, all the kind of difficult situations where you may not have seen before. So digital twins are super useful for that, because what you can do is you can attempt the data augmentation. So you use your real live data, but you can manipulate. You can add vulnerable road users. You can introduce this kind of pedestrian that would want to jump in front of you, or erratic cyclist, and the rest of it. And also you can obviously validate and test in new software. This is a just very small plug for the work we have done in this space. It's a project called NGCDI, and we developed digital twin for wireless, so specifically wireless network, also within the vertical of connected automated mobility, but taking a bit of a zoomed out view of this. So rather than developing a driving policy for one vehicle, is how you manage entire fleets of vehicles. How do you make sure that all these vehicles get the digital service in there? Another area I want to signpost is the softwareized future versions of wireless systems. Maria, in her presentation, made a very good case where we are headed in this direction, where we want softwareized, disaggregated new networks that will deploy Open RAN techniques. And Maria also mentioned several kind of examples of what that policy might be to run your Open RAN, and also real-time control techniques such as beam management or interference or this type of techniques. But what I want to say is you can also test, once you have digital twins, you can also test stress test. So your network, look for the weak points, and this could be due to the internal factors such as anomalies within the system, and maybe external intrusion, so IDS detection. And furthermore, it's actually becoming, you can see the confluence of the idea of digital twins and Open RAN. Open RAN, again, that's been said already, essentially that means software on a COTS, on a commercial off-the-shelf device. So once your network is running that, there's no problem to duplicate. It's just a software. You make another copy of the same software and run in a slightly different place. It's different instantiation of the same thing. So the digital twin becomes very easy to be hacked. And there's one more example I want to show. This is what you can do. Again, this is an attempt to answer the kind of ever-present question when various people are looking at connected automated vehicles is, will it be any better? What will be the benefit? And here's just one study. Again, I'm not going to go into details, but essentially the task or the question we asked was, is there any benefit in terms of traffic flows? If you have three groups of vehicles, so HD here is human-driven vehicle, AV is automated vehicle, CAV is connected and automated vehicle, is what are the differences if you have these three classes? And maybe I'll just quickly say what are the assumptions behind the simulation. Human-driven is what it is. AV assumes it's sort of similar to human-driven, but it cuts the reaction time. So we can assume, you remember from your highway code, you should keep 2 seconds distance to the vehicle in front. 1 second of that is due to reaction time. Automated vehicles have basically zero reaction time. And connected automated vehicle add the increased perception field. Through the wireless communication, they will be much more aware about the state of the road in principle, for 100 meters and kilometers ahead. So they can continuously replan the road. Okay, this is just quick slide. Yes, I should have warned you this would be a little bit geeky, but well, we're all geeks, so perhaps no need to apologize. This is just a numerical representation of how these systems would work. For this particular case, I'm not making any claims. This is the ultimate result. This is just a glimpse into this new world of future connected vehicles. We've picked up several cities. These results present only 3 cities, but what we want to show is connected automated vehicles can achieve a better average speed. So essentially, the traffic flows a little bit smoother and faster through the city. That's another quick area I want to mention is anomaly detection. Again, you need your digital twin if you want to test your anomaly detection systems and develop. In principle, you can use unsupervised learning techniques, and that's in fact what is being done in this study, but also by many others that have done similar studies. But in any case, at the end of the day, when you want to test how your system is picking up anomalies and IDS, so what you still need to know whether those have been picked up correctly or not. So you need to have a label at the end of the day for the testing stage. So again, in real world, this is really hard to develop anomaly detection, looking just at the real world data. In the digital twins, there is no problem. You can always inject and stress test any anomalies you want. This beautiful butterfly slide here, it attempts to show one technique that is being developed recently in AI, machine learning, called autoencoder network, which essentially takes the inputs on the left-hand side. This, you may recognize, this is Bristol, in fact, or rather roads of Bristol, roads and layout of Bristol, and it tries to learn a compact representation through this kind of squeeze in between of this butterfly network. And the idea is once we have a compact representation, we can then pick up anomalies, those that are look outliers in this compact representation. And that may be my final geeky slide that attempts to show that this strategy in fact does work. It is in principle binary hypothesis testing problem. So we have this situation where we want to trade false positive rates with true positive rates. So we want to minimize false positive rates, maximize true positive rate. You want to get curves that look kind of a little bit like square, so they'll go steep pretty quickly, and the area on the curve is maximized. So here what I want to say is standard techniques that are represented by this yellow and dashed lines. Dashed is actually it's a random decision. It's as worst as you can have. Yellow is state of the art, and a blue one is this new technique that is based on deep neural nets. And this is my, I believe, my final slide, where I want to point to yet another application. I've sort of alluded to it as I was going along, but I think is another important application where, well, we know that our networks, as we race towards these new techniques, we pile on all sorts of layers of software, or open run and everything else. There is, in fact, the network gets complicated in the architecture. Are we sure that it's all watertight? It's not exposing any vulnerabilities in the process? And the answer is, well, we cannot be really that sure. We're doing our best. This is We are building in security from start, but there is this residual thought that things may be left unchecked. And one way we can use your digital twin is to check for vulnerabilities in the network. And you can do two things at the same time. You check for vulnerabilities and plug the holes that you may have found and exposed, all in one go. And you can set it up as this adversarial game, where what we have is on the left-hand side, you might have malevolent agent, the bad guy that attempts to bring your network down. And on the right-hand side is the benevolent agent that attempts to counteract this. And you set it up as a game. One thing that I think should also be clear is that the future bad guys will not attempt crude attacks. They will also use state-of-the-art AI. I think this should be absolutely clear. So the only way to counteract this is to design systems that can spot that automatically, that can themselves think of attack surfaces that cannot be thought by a human. That's one way to achieve this. Okay, I've got one more slide. I just want to say a few words. Is it all that rosy? What are the challenges? Well, there are still challenges. One thing that you may have predicted is that digital twin needs to be a very good representation of the real system. Okay, so to make some predictions, to learn, you need to have your twin as good as the real thing. And as I mentioned, in some cases, actually, that task becomes easier and easier. Open Run is one of those areas, because you can make a twin with one press of a button. You still need to model your real world aspects of it, so propagation and the rest of it. That still is a challenge. But we've been doing that for many years in wireless community, so we should maybe not be petrified about that aspect. And I want to point out, what happens if you don't have the ideal twin? There's another few interesting areas that are happening in machine learning that can also come to rescue. And one is called transfer learning, and the other one is called the meta learning. And the idea in both cases was a similar idea, but what we hope to achieve is we want to have a situation, a twin, that will be able to be adjusted, tweaked, with just the minimum amount of well-curated data from the real world. That's essentially the idea. So, if we design our system well, and it can be refined in a very clever way, that's really good news. And that is my last slide, so thank you. And yes, I want to just give a shout to BT EPS as an Innovate UK for sponsoring some of the work that I have presented.